Hello, welcome to this lecture on molecular quantum chemistry. This lecture is actually the continuation of the previous lecture. Here I am going to discuss some of the questions that appeared in the previous year CSIR JRF net examinations. Okay, let me continue. This is question number 1. The lowest energy unnormalized wave function of H2 plus molecule is, where R1 and R2 are the distances between the electron and the nuclei 1 and 2 respectively. Okay, see, you can assume H2 plus ion as an hydrogen atom, is a combination of an hydrogen atom and an H plus. Okay, let us take this as atom A and this is B. Okay, so here you can assume this also as HA is plus and HB as a neutral atom. Okay, suppose if you take this case, in this case, see, this ion has no electron, so we should consider only the atom A. So in atom A we have the nucleus and we have an electron. Okay, let us assume this distance as R1. Therefore, for this possible combination, we have write the wave function as e power minus R1 by A naught. Okay, without considering normalization constants. Right. Similarly, if you see this case, in this case A is ion and B is an atom, neutral atom. So if you take this case, okay, the distance between the nucleus and the electron, let us assume this distance is R2. So what is the possible wave function? Hydrogenic wave function e power minus R2 by A naught. Okay, now, so there are two possible ways you can write the H2 plus ion wave function. Okay, so the actual wave function can be given as the linear combination of these two, right? So the linear combination may be addition combination or maybe subtractive combination. Let me first take addition combination here. See here, see, so first I will take the addition combination e power minus R1 by A naught plus e power minus R2 by A naught. This is one possible combination which gives you the wave function for the system. Okay, and what is the subtractive combination? Subtractive combination is e power minus R1 by A naught minus e power minus R2 by A naught. Okay, now if you analyze the energies of these, okay, suppose we plot energy versus the internuclear distance, okay, R. Listen, for this simple wave function e power minus R1 by A naught, okay, or e power minus R2 by A naught. For this simple wave function, let us call this wave function as just for our understanding purpose, I will take this as psi1, this as psi2 and this as psi3. Suppose if you plot this or this, okay, you will get a graph something looks like this. Okay, it goes to minimum and then increases. Okay, this is for psi1. If you take psi2 will go to minimum, large minimum and then increases. Okay, so this corresponds to the ground state of the system. Okay, where the curve reaches the minimum possible energy, right? And if you plot psi3, this is psi2 plot. If you plot psi3 graph will go like this. Okay, if you do calculation, listen, without doing calculation, I am giving you only the result, right? If you do calculation, you will get the same result. Okay, you can try also. Right, now listen, so this corresponds to an excited state wave function. So the wave function that corresponds to the ground state is this. Okay, in the case of hydrogen molecular ion, okay, the addition combination will give you the ground state of the ground state wave function for the system, right? So the correct option for this question is, okay, the correct option for this question is 1. Are you able to follow? Very simple, right? Then let me go to the second question. Yeah, this is the second question. The energy functional from a trial wave function is E alpha equal to alpha square minus 3 alpha by 6. The question is the variationally optimized energy is, okay, see, energy is given as alpha square minus 3 alpha by 6. You know very well alpha is nothing but variational parameter. Okay, if energy is given in variation in the form of variational parameter, okay, how to get the optimized energy? Optimized energy means the minimum energy possible for the system. Okay, yeah, now how to do that? You have to differentiate E, okay, differentiate E with respect to alpha, right? So if you differentiate E with respect to alpha, what we'll get? Keep the 1 by 6 as such. Alpha square, if you differentiate, you'll get 2 alpha, and 3 alpha if you differentiate, minus 3. Okay, listen, to get the minimum value, put this dE by d alpha as 0. Okay, we know very well, as see, this energy of the system depends upon the variation parameter. Okay, as you increase the variation parameter, the energy decreases, reaches a minimum, and then it goes like this. So to find the minimum, what to do? Differentiate E with respect to alpha and put the value equal 0, because at this point slope is 0, right? Now so if you use this idea, so put d by d alpha is 0, therefore 1 by 6 into 2 alpha minus 3 equal to 0. Okay, so 6 is in the denominator. If you bring it here, it becomes 0. So 2 alpha minus 3 equal to 0, or I can write alpha equal to 3 by 2. Okay, so when alpha is 3 by 2, right, the system reaches the minimum possible energy. So what is that minimum energy or the optimized energy? Substitute this 3 by 2. Okay, substitute this 3 by 2 in this equation. Okay, so I'll keep 1 by 6 as such. Okay, alpha square, you put alpha as 3 by 2 there. So 3 by 2 square minus 3 into alpha, alpha is 3 by 2. Okay, so 1 by 6 into 9 by 4 minus 9 by 2. Okay, so if you take LCM, I'll write here 4, keep 1 by 6 as such, right? 4, 9 minus 18. Okay, so 9 minus 18 is minus 9. So minus 9 by 6 into 4. Okay, 2 3s are 6, 3 3s are 9. So the answer is minus 3 by 8. Minus 3 by 8 is the optimized energy, okay, for this energy function. Okay, yeah, so the correct option is option 2. Minus 3 by 8 is the answer, right? So if energy is given in terms of variational parameter, okay, what you have to do? You have to minimize the energy. How to do minimization? Differentiate energy with respect to the variational parameter and put that value equal to 0. Okay, you will get a value for alpha where the system's energy is minimum. Resubstitute that alpha in the energy expression, you will get the answer. Okay, yeah, then I'll go to the next question. Yeah, see the question. The highest energy pi molecular orbital for allyl system is, yes, listen, allyl system. Allyl system means it can be a radical, or it can be a cation, or it can be an allyl anion. Okay, whatever it is. Okay, you'll get 3 pi molecular orbitals in this case. You'll get 3 pi molecular orbitals. I'll call this as psi1, this is psi2, and this is psi3. Okay, you know very well the ground molecular orbital where this value is 1. You know very well in general for Huckel molecular orbital of wave function psi n. Okay, number of nodes equal to n minus 1. Right? So if n is 1, that means there is no node. Okay, here we have 0 node, here we have 1 node, here we have 2 nodes. Right? Now just go through the question. The question is the highest energy pi molecular orbital for the allyl system is. This is the highest energy pi molecular orbital. Highest energy pi molecular orbital must contain 2 nodes. Okay, listen, see the first one. See here in this linear combination is given. Here we have plus sign, here I have plus sign. Plus to plus, no change of sign, so there is no node, 0 node. Then again see plus to plus, no change of sign, again 0 node. So the option A has no node. No node. Now I'll go to option B. In option B, you see here I have plus, here I have minus. So when you move from this part to this part, sign is changing. When sign changes, it indicates there is one node exists in the wave function. Okay, and see the third option, plus become minus. Here we have one node. Then minus become plus. Yes, we have another node. Sign changing, right? So this part of wave function or this wave function has two nodes. What about the fourth one? Here we have plus sign, plus become minus, one node. Minus remains minus, no node. So this is also having only one node. Okay, so by simple analysis we can easily find out, okay, the correct the highest energy pi molecular orbital for allyl system. Okay, so the correct option for this is 3. Why? Because the highest energy pi molecular orbital must contain 2 nodes in the case of allyl systems. Okay, it's very simple, right? Yeah. Next question. One of the Huckel molecular orbital of 1,3 butadiene is given. The energy of this orbital in terms of Coulomb alpha and resonance beta integral is. Participants, you try to remember this. This is very important. That energy for the ground molecular orbital is alpha plus 1.618 beta in the case of 1,3 butadiene. In the case of 1,3 butadiene, the lowest energy molecular orbital is alpha plus 1.61 beta. The second one is alpha plus 0.618 beta. Third one is alpha minus 0.618 beta. And fourth one is alpha minus 1.618 beta. Okay, so for some systems you can remember the values, right? Now listen. This molecular orbital, the given molecular orbital, okay, what is given? Phi is equal to 0.6 times into chi1 plus 0.37 into chi2 minus 0.37 into chi3 minus 0.6 into chi4. Okay, we don't know whether this wave function corresponds to ground molecular orbital or the first excited, second exit or third exit, that we don't know. But by observing the number of nodes, you can easily identify. See here plus sign, plus to plus, no node, plus to minus, yes, we have one node, minus to minus, no node. So it has only one node total. It has only one node, right? That means it corresponds to, this is psi1, here no node, this is psi2, yes, psi2 must have one node. So it corresponds to this energy molecular orbital. Okay, so what is the energy of this molecular orbital? Alpha plus 0.618 beta. Alpha plus 0.6, roughly 0.62 is there. So the option is 2. Okay, it's very simple. Listen, just see the molecular orbital, identify number of nodes. Okay, the number of nodes will give you which molecular orbital it is, whether it is the molecular orbital corresponds to ground state or first excited state or second excited state, we can easily identify. Okay, but the energy expressions that you should remember. Okay, for 1,3 butadiene, right? See, at least you just remember for ethylene, right? Ethylene, then for 1,3 butadiene, then cyclobutadiene, right? For this system, you try to remember the energy expressions, right? Then benzene. Okay, yeah. Now, so let me go to the next question. The term symbol for the ground state of B2 is boron molecule, B2. Boron molecule has 10 electrons. Okay, and what is the electronic configuration? Sigma 1s2, sigma star 1s2. Okay, then sigma 2s2, sigma star 2s2, then pi 2px, pi 2py, they have same energy. So we filled already 8 electrons. Okay, so the remaining are 2. So put 1 here. Okay, now listen, these are all filled molecular orbitals. They do not contribute. Okay, leave it. Now I'll take the final open shell orbitals. Now here both electrons are present in pi orbital. For pi bonding molecular orbital, okay, for pi bonding molecular orbital, lambda value, listen, so in boron molecule, these orbitals are filled molecular orbitals. We know very well filled molecular orbitals do not contribute. So let us consider the pi 2px and pi 2py molecular orbitals, right? Each consists of one electron. We know very well since pi 2px and pi 2py are degenerate, okay, the lambda value for one molecular orbital is +1 and the other molecular orbital is -1. So one electron is present here, the other electron is present here because we are talking about ground state. Okay, ground state should have highest multiplicity. So this is the possible configuration for the ground state, right? Now for one electron lambda value is +1, for the second electron lambda value is -1. Therefore the big lambda or capital lambda is sum of these two, +1 plus -1. If you add, the value is 0. If big lambda is 0 or capital lambda is 0, then the term symbol is sigma. Okay, then both electrons have a spin plus of, so total spin is 1. If total spin is 1, then multiplicity 2s plus 1 equal to 3. Okay, so it is a triplet state. Then we also know that for pi bonding, both are bonding molecular orbital. For pi bonding molecular orbital, okay, the symmetry is ungerade, right? So for electron 1 it is ungerade, for electron 2 also ungerade, because both are present in pi bonding molecular orbital. Ungerade into ungerade is gerade, right? Therefore the term symbol for this is, okay, triplet sigma gerade. Then we should put whether plus or minus. Remember, if the molecular orbitals are degenerate, okay, in the case of pi or pi star, right? If you have one electron in each of these molecular orbital, then you will get minus sign. It is antisymmetric with respect to the plane passing through the internuclear axis. Similarly, if you have any other system having one electron in pi star orbital, then also you will get the symmetry with respect to the plane passing through internuclear axis is -1. Therefore the term symbol is minus, not -1, it is minus. Yeah. So the correct term symbol is triplet sigma gerade -1, option 2. Okay, remember in the second period, boron molecule and oxygen molecule, these two molecules have minus state, sigma minus state for the ground state configuration. Okay, yeah, although for the ground state they have minus sign in sigma. Okay, next. So the correct option is 2. Now let me go to the next question. One of the correct normalized sp2 hybrid orbital is, yeah, sp2 hybrid orbitals are given here. We have to identify the correct normalized sp2 hybrid orbital. Listen, it is given normalized. Remember, if the hybrid orbital is normalized, it means sum of the squares of the coefficients, should be equal to 1. And second important information, since it is an hybrid orbital, okay, we know very well s orbital contribute equally. S orbital contribute equally in all hybrids, in all hybrid orbitals. This we know. Okay, what does it indicate? Listen, so that means the coefficient corresponds to s orbital. Okay, this is coefficient corresponds to s orbital. That should have the value 1 by square root of, okay, how many atomic orbitals that combine and form the hybrid orbital. Okay, say for example, for this question, sp2 hybrid orbital is given. Okay, so here one s orbital and two p orbitals combine and form sp2, so n value is 3 here. Therefore the coefficient corresponds to s orbital. Keep this in mind. The coefficient corresponds to s orbital should be 1 by square root of 3, right? So keeping this in mind, listen, see in option A, this is the s orbital and the coefficient is 1 by 3, so this is wrong. Okay, coefficient should be 1 by root 3. So second option, if you see, listen, coefficient is 1 by 2 is given. see the s orbital coefficient. Okay, so here the s orbital coefficient is 1 by root 3. Yes, this may be correct answer. Similarly, third one, s orbital coefficient is 1 by 3. Okay, 1 by root 3 supposed to be there. So just by analyzing this information, we can identify the correct option. So the correct option for this question is 1 by root 3 into phi 2s plus square root of 2 by square root of root 3 into pi 2px. Okay, whether it is normalized or not, how to check? Take the coefficient 1 by root 3 and square it, then take other coefficient square root of 2 by square root of 3 square. Okay, find the value. 1 by root 3, if you square it, you will get 1 by 3. Root 2 by root 3, if you square it, you will get 2 by 3. So you will get the answer as 1. So it means this orbital is normalized as well as the s orbital coefficient is 1 by root 3. So the correct option for this question is 3. Okay, it's a very simple one. Now let me go to the next question. The electronic transition energy from pi 1 to pi 2 in propenyl radical. Yeah, this is propenyl radical, allyl radical, is 4.8 electron volt. Okay, it is given pi 1 to pi 2 is 4.8. Okay, within the framework of Huckel theory, the transition energy from pi 1 to pi 3 would be. Okay, so they are asking what is the transition energy for pi 1 to pi 3. So you know very well, for allyl system we have 3 molecular orbitals. Okay, this is let me call this as pi 1, this is pi 2, this is pi 3. What is the energy of this molecular orbital? Yeah, we know very well, it is alpha plus root 2 beta for allyl systems. Okay, energy of the middle one is alpha, energy of the highest molecular orbital is alpha minus root 2 into beta. Okay, now listen, in the question it is given that pi 1 to pi 2 is given. Okay, pi 1 to pi 2 energy is 4.8 electron volt. Okay, this is given. Now we should identify what is the energy corresponds to pi 1 to pi 3. This we have to calculate. Okay, so listen, for pi 1 to pi 2, the energy difference. The energy difference for pi 1 to pi 2 is, listen, higher energy value is alpha minus lower energy is alpha plus root 2 into beta. So alpha cancels, so you will get the answer as minus root 2 into beta, and this value is given as 4.8 electron volt. Okay, keep this as such. Now we need to calculate delta E for pi 1 to pi 3. Pi 1 to pi 3. So what is the difference? Higher level energy is alpha minus root 2 into beta minus lower energy is alpha plus root 2 into beta. Alpha cancels, minus root 2 beta. Here also you will get minus root 2 beta. So minus if you add, you will get minus 2 root 2 into beta. Or we can write this as 2 into minus 2 root 2 beta. Listen, minus 2 root 2 beta is 4.8 electron volt. Then 2 into minus 2 root beta is 9.6 electron volt. Very simple question, right? So the correct option for this question is 3. Okay, yeah. Yes, I have discussed some couple of examples, right, that exist in the previous year CSIR JRF net examinations. I'll come out with a few more questions in the next class. See you then.